Okay, so now we're back to Terry Tao's equation. Remember, we have 1/60th, which is how long it took the Earth to go, or the minute hand to go around.
Yeah.
Minus the slower one, which was the
hour.
hour hand, which is 1/60 times 12, equals 1 over the unknown that we were looking for. That's just what Terry Tao's equation was saying here. So we had an equation that looked just like this, right?
Yeah.
Omega is 1 divided by how long it takes to go around. So just remember, like we had 1/60th, like I just said, minus 1 over 12 times 60 was 1 over t. That was our equation.
Yeah.
Here we have, how long does it take the Earth to go all the way around the Sun?
365. 365.25, actually.
Okay, if we want to be super precise, we can say 365.25. Takes an extra quarter of a year.
Yeah.
That's
quarter
why.
Of a day.
Quarter of a day. That's why every 4 years we have a leap year.
Yeah.
Okay, so we have 1 over 365.25 minus 1 over x, however long it takes Mars to go around, equals 1 over 780. And this is where the 780 came from, is the astronomers noticed that every 780 days Mars looked the same. It was in the same place above the horizon, and they had made these measurements, according to Terry Tao, for like 1,000 years.
Wow.
And it's actually incredible because
They didn't really have any technology. No.
they had no technology. They didn't even have telescopes yet. This Copernicus calculation was done in the 1500s. Telescopes were invented in the 1600s. So they were just looking out. But they still noticed about every 780 days Mars was doing the same thing. And that's because, this is what Copernicus said, well, the Earth's going around the Sun, Mars is going around the Sun, so they must line up at some point, and then 780 days later, which is almost 2 years, right?
They line up again.
Right. 365 times 2 is, it's more than 2 years later, sorry.
Yeah.
They line up again. Okay, so the Earth goes around twice, Mars goes around once in a little bit, and they line up. Okay, so now we have to solve this equation. How are we going to do that?
Well, let's bring the 365 to the other side. This 1 over 365.
Okay, so I get minus 1 over x equals 1 over 780 minus 1 over 365.25. Okay. What would you do now?
Well, getting a common denominator would be tough.
Getting a common denominator is going to be tough. So in fact, I think we'll just do it with our calculator. Okay, so 1 over 780. Oops. 1 divided by 780 is 0.00128. 128,205 minus 1 over 365.25 is 0.00273785.
And now
I subtract them and I get, this side is minus 0.0014558.
wow.
So I have minus 1 over x equals minus 0.0014558.
Well, let's get rid of the
Let's
minuses.
get rid of the minuses. Multiply both sides by minus 1, and now what?
Well, now we need this if we could get x in a decimal form. Well, because x is this, it's flipped though.
Okay, so now I just take the reciprocal of both sides, and I get 687 approximately days. And this is the math that Copernicus did.
Wow. So it's almost 100 more days to go around, and then they line up.
Right. So the Earth goes around twice. Mars goes around once plus a little bit, and they line up again. But this 687 days was an amazing calculation by Copernicus. And it came just from exactly the calculations we did with the clocks.
Wow.
And so that little simple equation that Terry Tao wrote down is just like the equation we have for the clocks, right?
Yeah.
And then the math works out just that way. And that was, what, 500 years ago?
Yeah.
With no telescopes.
No.
They figured out just from the same way we would figure out when clock hands were on top of each other. Instead, they knew when they were equal.
Wow.
They knew how long the Earth took to run around, so they had one extra thing and they solved for it. And they figured out how long it takes Mars to go around the sun. Pretty cool, right?
Yeah. Yeah.
Alright, there you go. Good job, guys.
Clock math.
Clock math.